Hi. In this video, we'll see how to use present worth and future worth to compare between engineering alternatives. And we've seen in previous video the process for comparing between engineering alternatives, and we start with defining the alternatives first and their planning horizon, developing their cash flows, and then determining their time value of money. And the comparing between alternatives, we knew that there's the present worth method, future worth, annual worth, and also there's the internal rate of return method. So in this video, we're covering two of these approaches to compare between alternatives. Present worth, we've seen it in dealing with different types of multiple cash flows and series of cash flows. But the idea here is for every alternative, we will calculate its present worth, bringing the worth of every cash flow in that, or every amount of money in that cash flow to the present, using P given F or P given A or P given G factors we have. And we use that present worth of every alternative to compare between our alternatives. And it will be like on a basis of apple to apple or like to like kind of basis. So we are trying to be fair, representing each alternative as a value, as a quantitative value, but it's at the same point where I calculate the worth or value for any other alternative. So for here, one thing we need to make sure is we're using the least common multiple lifespan. So we have to, like we covered in the previous video, if the alternatives can be renewed, then it's better to use them for the same, or kind of draw the cash flow expanded for the alternatives to fit that common lifespan or planning horizon. Future worth is the same, similar thing, but you just, instead of calculating the worth in the present, you calculate it into the future, which is the terminal point in the cash flow that we have for each alternative, meaning that it's the end of the last year of the cash flow. The same condition applies if the alternatives are renewable. This means that I will look for the least common multiple number of years to be my planning horizon. So let's explain the use of both methods in this example. We have two types of structures. They have different first costs. They have different lifespans. Structure Y has no salvage value, meaning that if it reaches the end of life, I don't get any money out of it. But the structure Z is a little expensive, but you get around $1,800 out of this structure when it's being salvaged. And there is a maintenance cost every year also, and different values. So part A, we need to compare between the alternatives using present worth, and part B is using future worth. So if we draw the cash flow, or you apply here the first method, which is present worth, I need to figure out the least common multiple. We have 12 years and 24 years. So the least common multiple here would be 24. So this means that if I'm starting with structure here Y, so actually that's, let's see, so that's, yes, structure Y has 12 years useful life, but over 24 years, I will use it twice. So it will have two cycles. I will have two cycles of ownership for this type of structure. So the initial cost, $4,500, annual cost of $1,000, and there's no salvage cost at the end. So at the end of the 12th year, I will put that arrow representing my maintenance during that 12th year, but at the end of it. And then right after that, or during the same time, I will buy a new structure. It will cost me $4,500, and then at the end of the year of the new cycle, which is the 13th year, I will start having these maintenance values. So we will start calculating here the present worth of that alternative. So the first 4,500 year is already in the present, so I multiply by 1. And then the $1,000, I multiply by P given A 5%. And let's pause here a little. Some of you would say, like, I have $1,000 from 0 to 12, and then from 13 to 24. But is there really a gap between in this point? So is there really a gap here? So the arrow that's at 12 is representing year 12. The arrow at 13 is representing year 13. So we really don't have a gap here. It's kind of a one big series of maintenance costs here. So 24. My end year is 24, not 12. I'm combining both $1,000 per year for the first and the second cycle. And then the last part I will add here is the 4,500 initial cost of the second cycle of that structure. So we'll figure out the values of these factors from the tables or the formulas, and we'll end up with this present worth of structure Y to be around 20,800. Now we're moving to structure Z. It's one cycle because its life span is already 24 years. So I'm not like demolishing and buying or getting a new one. But at the end of the 24th year, I will salvage this structure for $1,800. And then I will calculate the present worth here. Similar process to what we have seen, just one less term compared to structure Y, because I don't have that transition from cycle 1 or cycle 2 or buying a new cycle. Here we have P given F for 24 years, moving the 1800 in the future. And remember the signs here. So 1800 is the only positive cash flow we have, and everything else is negative. So if I bring the values of the factors, I'll find my present worth to be 19, and it's a negative $19,376. So by comparing, both are negative means there are both kind of present worth of costs, because I'm not showing what value that structure will create, or so like I'm only focusing on reducing costs, or I'm focused on selecting the one with the least expensive option. So in this case here, Z is the least expensive, so I will choose structure Z. So all of that is just approach, the present worth approach, which is part A of the problem. Now part B, it's kind of a repetition of what we did, but we are now calculating the worth at the future, not the present. So using the future worth, structure Y, you see here we're doing exactly the same thing, drawing the cash flow, repeating the cash flow over 2 cycles, and even the terms will look the same, but one thing to pay attention to is that the 4,500, when I calculated its present worth, the one at time 0, it was multiplied by 1, but now it's multiplied by F given P 5% at 24. So I move its value all the way from 0 to 24. And now all the factors are F given something, F given P, F given A. Calculating the factors or getting them from the tables, that will give us the future worth of Y would be equal to 6796.3. Moving to the next, the structure Z, drawing the cash flow, and calculating here my future worth, 10,000 times F given P, and then the annual maintenance, F given A, moving into the future, and then 1800 here, salvage value is already in the future point I'm calculating the worth at, so it's multiplied by 1. Bringing the values of the factors, and then we'll find that the future worth of structure Z is 62 492.4. So you see both are also positive, negative. Focusing here on selecting the least expensive option, I will end up with the same conclusion that I got from the present worth approach. So I'll also choose structure Z. So regardless of the approaches you use, you should end up with the same economical conclusion of which one should be selected from the economics perspective. And one thing actually that I would like to note here verbally is I didn't have to do all the detailed calculations that I had I've shown for future worth. If I know the present worth of each alternative, I can right away calculate the future worth of it using the F given P formula. So I didn't have to go over in detail like that. If you are confident about the present worth value you got from part A, you can recycle that and multiply it by F given P, so you end up with the future worth. But I'm showing here the details just as a practice and to show the difference between calculating the worth of a cash flow in the present and in the future. That's it. Take care and stay safe. Bye.